Amazing. Hello, everyone. Thank you all so much for coming. It's so nice people giving up their Saturday nights to hear about the mysteries of the universe. So I'm going to spend the next hour or so trying to convince you of something which is on the surface completely ridiculous, right? That most of the universe is missing, that the majority of the universe is made of some strange stuff that we have never been able to see or detect in any way, which on the surface of it sounds more like faith than science, right? And so the reason I wrote this talk originally is because I wanted to lay out, like from the beginning, the reasons that we think this and sort of present you the evidence bit by bit, so you too can believe something ridiculous, that most of the universe is stranger than we can even imagine. So the story really starts with galaxies. So I'm sure for this audience, I don't need to introduce the idea of a galaxy too much, but in case, this is a galaxy. This is a famous galaxy. This is a representation of what our Milky Way would look like from the outside. And the story of dark matter really starts with the idea that galaxies weigh too much. Galaxies don't weigh what we would expect. Now, you're all thinking something very obvious, which is, well, how on earth do you know that? How do you weigh a galaxy, right? You can look at them and they look very pretty. How do you get an idea of how much a galaxy weighs? And the answer really is that we use gravity. But to sort of build up to the answer, I just want to sort of like break things down a little bit, bring things down to earth, and then reach the answer. So we can forget galaxies for a moment and just think about, I'm going to take you back to your primary school science and think about the Earth going around the sun. So the Earth goes around the sun, hopefully not a shock for this audience. Luckily, because we know how gravity works, we can look at the Earth going around the sun and use that to understand how much the sun weighs, right? We can look at the sun's gravitational influence on the Earth and ask the sort of simple question, how much would the sun have to weigh in order to exert this type of gravitational influence on the Earth, right? Luckily we understand gravity very well. I'm based in Cambridge, so I always have to remind people that gravity is a Cambridge invention, thanks to Mr. Newton. We can watch the Earth going around the sun. We know that we are about 150 million kilometers from the sun. We go around in a year. You put your numbers in. This is the only equation in the talk, I promise. You put your numbers in, and you get the answer that the sun weighs this ridiculous amount, right? 2 followed by 30 zeros kilograms. And the really, really important thing is that we don't have to see the sun to reach this answer, right? We don't have to know anything about the sun. All we have to see is the Earth going around and round. We're 150 million kilometers away from something. We're whizzing around once a year. Our knowledge of gravity would tell us that whatever that thing is that's pulling us around weighs this amount. And this technique was actually used very recently. The Nobel Prize in Physics was awarded to some astronomers that looked into the center of our galaxy and saw stars just orbiting nothingness. And they did the same trick. They did the gravitational maths and figured out that whatever is sitting at the center of our galaxy and pulling these stars around has to weigh a few million times the mass of the sun. And so it has to be a black hole. You can use gravity to weigh things even if you can't see them. There's 2 important pieces of this puzzle that we'll need for our toolkit, if you like, going forwards. First of all, the speed of whatever is orbiting around increases with mass, which hopefully makes a kind of intuitive sense, right? You make the sun heavier, gravity gets stronger, it's going to pull Earth around more quickly. The second one is that the speed decreases with distance. So if you're very up and close to your gravitating thing, you're going to be pulled around very, very quickly. The further away you get, the more weakly you feel the effect of gravity, and you're going to be going slower and slower. And we actually see that in our solar system. We're whizzing around at about 67,000 miles an hour as we speak, which is one of my favorite facts. If you're closer, Mercury is going around at about 100,000 miles an hour. It's closer to the sun. It's feeling its gravity more strongly. Once you get out to the outskirts of the solar system, something like Saturn is going at about 20,000 miles an hour. Neptune is going at only about 10,000 miles an hour. The further you are away from something, the weaker you feel the gravity, the slower you go. Okay, so we have our toolkit. We understand how to weigh things using gravity. We can now move on to galaxies. So galaxies are spinning. Our Milky Way makes one big orbit every couple of 100 million years. But the reason galaxies are spinning is because every single star inside the galaxy is orbiting around the gravity of the galaxy, right? Just like Earth orbiting around the sun because of the sun's gravity, the sun is orbiting the center of the Milky Way because of the collective gravity of all the stars in the Milky Way. So if we want to weigh a galaxy, we can just do the same trick. You just pick some stars on the outside of a galaxy and see how quickly they're being pulled around, and that should tell you how much the galaxy weighs. In reality, it's a tiny bit more complicated than that because in general, we can't actually see individual stars. So what we can do is we can just take a series of measurements of the sort of the flow of the stars. It's a bit like, if you want an analogy, it's a bit like using a series of weather stations and taking wind readings and using that to build up a picture of a storm or a hurricane, right? You get the idea. And again, because we understand gravity very nicely, we know exactly what we expect to see. The stars in the inside of the galaxy are like galactic mercuries. They should be pulled around really quickly by the sort of the proximity to the galactic center. And once you get all the way out here to the galaxy's edge, these are like the galactic Neptunes that should be going very, very slowly. So we know exactly what we should see. And the total weight of the galaxy is determined by the sort of the height of this graph. So this is what you should see. It is, in fact, we don't see this. This is exactly what you do not see. When you make this measurement, you see something completely bonkers. You see that essentially every star in the galaxy is being pulled around at the same speed as those inner stars, which seems kind of ridiculous on the surface. It seems like gravity is broken. It's a bit like if you looked at our solar system and you saw Neptune whizzing around just as fast as Mercury. Like that would just completely violate every law of gravity that we know about. But that is what galaxies are doing. It's very, very strange. So the first person to notice this was an astronomer called Vera Rubin. And the reason she went down in history is not just because she made this very important measurement. She also came up with an answer. She explains this by saying, well, what if the galaxies that we actually see are a very, very small part of the total system? What if the galaxy we actually see is something like a pearl sitting in an oyster? If there's a big cloud of invisible, heavy stuff all around the galaxy, then the reason those stars are moving too fast is because all this invisible, heavy stuff is pulling them around. Remember the two rules in our toolkit, right? Speed should decrease with distance, and because it's not, we have to invoke the other rule, that speed must be increasing because there's heavy stuff, even though we can't see it. And so Vera Rubin said, okay, what if these galaxies are all encased within these clouds of invisible stuff? That would perfectly explain how they're being pulled around. So this was in the early 1960s, and this is when the idea of dark matter really sort of exploded onto the scientific and public stage. Interestingly, it wasn't the first time it was ever proposed. The idea was originally floated back in the 1930s with this guy, Fritz Zwicky, who is like the spitting image of Robert De Niro, right? So Fritz Zwicky was observing clusters of galaxies. He was working on the Coma cluster, which you can see here. To imagine a cluster of galaxies, you got to sort of imagine a galaxy and then mentally zoom out until you see an entire swarm of galaxies. Imagine like a swarm of bees where each bee is a galaxy, hundreds or thousands of galaxies all sort of moving around under the gravitational influence of the cluster. And what Zwicky noticed was that these galaxies were moving too fast. He measured how fast they were whizzing around, and it just could not be explained by all of the stuff in the cluster. And he even said in the 1930s, what if clusters contain some invisible stuff, some dark matter that's pulling these things around? People did get a hope that the problem had been nicely solved once we invented X-ray telescopes. It turns out that clusters are full of hot gas that glows very brightly in X-rays. And that it outweighs the galaxies, right? If you'd had a pair of scales and you put the hot gas in a cluster on one side and the galaxies on the other, the hot gas is heavier, but even that doesn't solve it. You add up the hot gas and the galaxies, it's still not enough to explain this strange behavior. So yeah, Zwicky was a bit of he was, I think, what in the 1930s was referred to as a character. He famously called his colleagues spherical bastards because they were bastards whichever way you looked at them. So he wasn't necessarily the easiest person to work with. But nevertheless, yeah, he came up with this idea. But this, at this point, it was just sort of shelved as a quirk of cluster astrophysics, right? We didn't really understand how clusters worked. But yeah, it seemed that clusters were heavier than they seemed. Okay, we just shelve it as with the rest of the mysteries about clusters. But then Vera Rubin comes along in the 1960s, and it turns out this strange dark matter isn't just confined to clusters, it's everywhere. Every single galaxy that we've seen in the universe seems to be full of this dark matter. They're all spinning too fast, including the Milky Way, by the way. It means that the sun and the solar system itself should be surrounded by this dark matter. It becomes a lot more of a pressing problem. And basically, the second half of the 20th century of astrophysics is just discovering this fact again and again and again. Everywhere we look, the universe is full of this strange stuff that we can't see. One of my favorite examples comes from what's called gravitational lensing. I'm sure lots of you would have seen this photo before. This is the first photo ever released by the James Webb Space Telescope. It's a beautiful example of gravitational lensing. Because this is the Royal Institution, I wanted to sort of do a practical demo, so I have brought along a gravitational lens. So this is a representation in glass of the warping of space-time around a heavy galaxy. The way gravitational lensing works is thanks to Einstein's theory that we understand that heavy things warp space and time, and the warping of space and time can act like a lens. As light travels through this distorted space and time, it gets bent. And so this is a representation in glass of the distorted space-time around a heavy galaxy. Now I'm going to hope the technology gods are smiling on me and swap the HDMI to this. And so what I'll be able to show you is how the gravitational lensing effect works. So we have here, so this is our nice flat space-time. And then as our gravitational lens passes over, you can see it gets distorted. Isn't it good? And so when we look at a heavy object, we see the space and time around is distorted just like this. You get an even better effect if you use, instead of a grid, use a picture of the distant universe, a picture of some galaxies. If I pass the gravitational lens across it, you'll be able to actually see objects being distorted. And if we get the alignment just right, we should be able to see a nice ring, which is something that we see in the actual universe. So this is the exact effect that we see when we look at wide clusters in the distant universe and around heavy things like galaxy clusters. And so if we go back to the real version, that's what you're seeing here. So the white fuzzy thing in the middle is a I was going to say nearby. Nearby becomes a bit of a flaky term with astronomy, right? It's only a few billion light years away. The white fuzzy thing is a nearby cluster, and the streaks and arcs you can see around it are much, much more distant. They're galaxies that the light has been distorted by the heavy cluster in the foreground. This is another one. This is one of my favorite. It's called the cosmic horseshoe for sort of obvious reasons. The blue thing would actually look very similar to our Milky Way if we were close to it. But this fuzzy red thing in the foreground has just completely distorted it and bent it into this sort of arc shape. The reason I'm talking about this is because, again, thanks to Einstein, we understand how heavy things warp space and time. And so we can look at a picture like this, or a picture like this from James Webb, and we can ask the question, how heavy is this thing in the foreground that's doing the bending? And again, it turns out to be much, much heavier than it looks. Every single gravitational lens that we see is telling us that there's way more mass there than we can actually see, right? There's some matter there, but it's dark, right? Again, it just comes up in every single field of astronomy. There's a nice little technique here. Again, it's another one of our techniques for our toolbox that we're going to need in a moment. So this is what astronomers call strong gravitational lensing, where the light is just completely distorted out of all recognition by some incredibly warped space and time. But of course, everywhere in the universe contains matter. And so the background space and time fabric of the universe is ever so slightly wrinkled and bumped everywhere. And so any beam of light traveling through the universe is going to pick up little distortions. And so there's a technique we can use called weak gravitational lensing, where we can sort of look on aggregate at all these distortions and we can paint a picture of where the heavy stuff is in the universe. This is how the basic idea goes. If we have a population of galaxies that looks like this, if we observe on the actual sky something that looks a bit more like this on the right-hand side, you can sort of see that, down there in the bottom right and sort of towards the top, there is something that is distorting the overall shapes of those galaxies, right? And this technique doesn't work if you look at one individual galaxy. But if you look at many, many, many galaxies in like a statistical way, you can say there is something heavy in this part of the sky that's doing some distorting. So this is called weak gravitational lensing. And it's a really, really nice technique for finding more dark matter. We can look at this. This is another cluster of galaxies. We do our statistical weak lensing trick. We look at the shapes of the galaxies, and we can just literally paint on where the heavy stuff is in this picture. And you can see it turns out that there is some heavy stuff in the middle where you would expect, but there's also a whole bunch of heavy stuff around the edge. Even though there's no visible matter there, again, there is dark matter. There is heavy stuff that we can't see. So I've said a few times now, like, this technique works because we understand gravity, right? We look at galaxies spinning around, and because we understand gravity, we can tell that there's heavy stuff that we can't see. Or we look at gravitational lensing, and because we understand gravity, we can tell that it's heavier than it sort of should be according to our images in our telescope. What if we don't understand gravity, right? That's the sort of million-dollar question, because we've been wrong about gravity before. If you were here at the Royal Institution in the sort of 1850s, 1860s, you might have had an astronomer talking about one of the most sort of strange astronomy phenomenon of the time, which was the orbit of Mercury around the sun. By then, we understand Newton's laws very well. We knew how planets behaved as they moved around in the solar system. And we were tracing Mercury's orbit around the sun, and it wasn't behaving as Newton's laws said it should. Instead of just going neatly round and round and round, it was tracing out a sort of spirograph pattern in a way that was very hard to explain. And to start with, some people had the idea that maybe there's a hidden planet that we can't see. They even invented a whole planet called Vulcan. And they said, well, maybe there's a planet that's so close to the sun and we can't see it, and the gravity of this invisible planet is pushing Mercury around in some way. But of course, there's no such thing as Vulcan, right? The reason Mercury was behaving weirdly was that we didn't understand gravity. It took Einstein to come along and rewrite the laws of gravity. And then using the theory of relativity, we can perfectly explain Mercury's orbit. So there was a situation, right? So the 1850s problem was, we have this theory of gravity. The universe isn't behaving according to the theory of gravity we expect. We have to just go and rewrite the theory of gravity. And now, in 2025, we have our theory of gravity. The universe is not behaving as our theory of gravity expects, and we say there's something wrong with the universe, right? So, why can't we just say, well, there's something wrong with the laws of gravity? So people have been doing this for years. It was first invented, there was a guy called Mordecai Milgram who came up with what he called MONDS, which stands for Modified Newtonian Dynamics. And basically the idea is you take your laws of gravity and you just tweak them ever so slightly. So what Milgram did was he added an extra little component to gravity that only kicks in when accelerations are really low. So in dense, speedy environments like the solar system, gravity behaves exactly as you would expect. But in very, very low acceleration environments, like, for example, the outskirts of galaxies, gravity is a little bit stronger than you would expect. And so it only takes this little tweak to the laws of gravity to completely match the behavior of galaxies. So why aren't I here telling you that the laws of gravity aren't what we expect? Why am I here telling you that dark matter is probably the answer? So for the longest time, these two were just competing theories of the universe. Do we live in a dark matter universe, or do we live in a universe with no dark matter where the laws of gravity aren't quite what we expect? And the reason they were competitors for so long was really just because there was no way to test between the two. This modified Newtonian dynamics theory was literally invented to explain the same thing that we caused the dark matter theory, right? What we wanted was some sort of observation that would let us distinguish between the two. And luckily, nature was very kind to astronomers and gave us an observation that let us distinguish between the two. So this is called the bullet cluster. So you've got to think back to what I said about clusters. Imagine sort of like hundreds or thousands of galaxies all sort of moving around together. The bullet cluster is a fairly unique system, actually, where instead of one cluster of galaxies, it's actually two clusters of galaxies. And they're moving together. And in fact, they crossed each other. They passed through each other a couple of 100 million years ago, and now they've passed through and out the other side. I've prepared some very high-tech graphics, which will help explain this. No expense was spared. There you go. So what we actually see today, these two clusters of galaxies, like over here, and they've passed through each other and out the other side. Now, galaxy clusters don't just contain galaxies. Remember that galaxy clusters also contain this hot gas. And the hot gas is going to behave slightly differently. So the reason the galaxies themselves can just whiz through and go out the other side is because the galaxies are basically collisionless. They are acting like individual fish in a shoal of fish or something. They can pass through, out the other side. The fish themselves aren't crashing together, right? They're just passing through the gaps very nicely. The galaxies are what we call collisionless. But the gas is not collisionless. The gas will experience frictional forces and get tangled up in the middle of the collision. And so what we actually see on the sky is something like this. The galaxies have been sieved away from the gas. In the center, there's a kind of a tangled mess of all the hot gas that have got sort of dragged apart by friction. And then on the outskirts are the galaxies themselves that have been separated. So this is really what astronomy was waiting for, because this finally lets us test the difference between MOND and dark matter. And the reason being is that they finally predict different things. So the fundamental question that we ask when we look at these clusters is, where is the heavy stuff? Where is the weight in this system? So dark matter, of course, tells you that the universe is made of gas and galaxies, but also dark matter that outweighs everything. And for reasons that I'll get onto towards the end, we also expect the dark matter to be collisionless. So the dark matter theory predicts that all the heavy stuff should be hanging around with the galaxies themselves. But MOND, remember, says there's no such thing as dark matter. All we have is the stuff we can see, which is galaxies and gas. Remember, the gas outweighs the galaxies. So MOND tells you that all the heavy stuff, like the center of mass, should be basically in the middle, tangled up with the gas. And so what we can do, we can take the bullet cluster, we can do our weak lensing trick, remember, which lets us paint on where the heavy stuff is, and that will tell the difference. If the weak lensing reveals that the heavy stuff is stuck in the middle with the gas, then MOND wins. If weak lensing reveals that the heavy stuff is on the outskirts with the galaxies, then dark matter wins. And obviously you've already guessed, because the talk is all about dark matter. But yeah, and sadly for MOND, it's kind of a slam dunk. So this is the bullet cluster. The background picture is the optical image of the galaxies themselves. The pink is the X-ray image showing you where the hot gas is. And the blue is the mass that's been painted on using this weak lensing technique. And it's exactly what you would expect if this strange, mysterious dark matter is in fact real. All the heavy stuff has been separated away from the gas. So yeah, people do still work on modifying modifying gravity, but like the overwhelming consensus is that dark matter really is a real thing. There's one more piece of evidence I really want to talk about before we try and solve the mystery of dark matter tonight. And the reason I like it so much is just because it's a completely independent line of evidence that just completely confirms everything we've been seeing in the rest of the universe. So all of the things I've been talking about so far with the galaxies and the gravitational lensing, this is all the late universe. We're looking around the universe about 13 billion years after the Big Bang. But we also see evidence for dark matter when we look back in time 13 billion years to the very start of the universe. And when we see something like this. So I'm sure lots of you will have seen a picture like this before. This is what we call the cosmic microwave background. You can think of it as like the echo of the Big Bang, right? Or the universe's baby picture. It's what the universe actually looked like when it was about 380,000 years old. So it's before planets, before stars, before galaxies, before atoms even. At this point, the whole universe is as hot as the surface of a star, just sort of expanding outwards into the dark. It's a temperature map, so the red bits are the bits that are slightly hotter than average, and the blue parts are the parts that are slightly colder than average. And the nice thing, I know it looks like a slightly Jackson Pollock-y modern art picture. The nice thing, if you know enough maths and if you know enough physics, you can basically read the whole future of the universe in this picture. The patterns you see in this picture encode a huge amount of information about what the early universe was like. And when we make our best observations of what the patterns are doing and the conditions in the early universe, we see dark matter. We see evidence for dark matter. I do realize at this point I'm basically asking you to read tea leaves, right? Just like, we look at these patterns, trust us, dark matter is there. So I do want to break down actually how we do this observation. So what we want is a way of mathematically sort of capturing the patterns here in this cosmic microwave background. It's very pretty, you can hang it on your wall. We want something we can actually do some analysis to. And so the technique we use is essentially a way of sort of capturing the patterns. What we do, we first of all look at this thing on the biggest scales of all. Imagine fuzzing your eyes, so you lose all the small detail and you only look on the biggest scales. And then we shrink our focus and shrink our focus and shrink our focus. And at each scale, we ask the question, how big are the patterns that are about yay big, basically? So we start off by looking at it on the biggest scales, and we say, okay, how strong are the really big patterns? Then we narrow our focus. How strong are these patterns? How strong are these patterns? How strong are these patterns? And then we put that all together. And then we put that all together on a graph, right? So you have size of pattern from the really big ones down to the really small ones, and then how strong they are. And when you do that, you get this very nice wobbly line here. I realize this is a little bit obscure. So the team that actually got this result were called Planck. They put together this really nice video. I think this is generally one of these sort of pictures worth 1,000 words types things. So this funky wiggly line that I just showed you is called the power spectrum of the cosmic microwave background. And so what they're doing here in this video is actually separating out those different scales, like I spoke about. So down here on the very left-hand side, the one wiggling, that is the cosmic microwave background if you only look on those biggest scales of all and you ignore all the fine detail. Then you slightly narrow your focus and you can see these patterns are not particularly strong. These are the patterns that are 10, 20 degrees wide, not very strong. So we slightly narrow our focus again. These are the patterns that are about 2 degrees big. Again, not super strong. This next one, these are the ones, there's loads of them, the patterns that are about a degree apart. All that sort of fine and granular detail is these ones. And the point, of course, to take is that the actual CMB that we see is the combination of all of these. It's the big ones and the medium ones and the small ones and the tiny ones, all added together, makes the whole CMB. This video always goes on like 10% longer than I wanted to. I'm going to leave it going because it's going to be very satisfying. They're all going to fly together and actually make the CMB. It's going to be great. Drum roll. There you go, wasn't that great? And so this is what we actually see. So the red dots are what we actually measure in the real CMB. So that's what we actually observe in the universe. The green line, the way we get the green line, we don't just sort of like freehand it through. The way we get the green line is by making what we call a cosmological model. You can imagine it like simulating universe. Imagine you're sitting in front of a big computer terminal and you can simulate a universe, and based on the conditions in the universe, the CMB looks different. You can imagine having lots of different dials, like the age of the universe you can turn up or turn down, or the size of the universe, or the curvature of the universe. And you turn these dials up and down, and it makes the CMB look different. And it turns out there is one and only one setting to all of these dials that actually matches the patterns that we see. And so this is how we know things like the universe is 13.7 billion years old, because one of the dials on your universe computer is 13.7 billion years old. And if without that setting, you can't match the data we observe. This is how we know things like the curvature of the universe and the composition of the universe. And luckily, one of the dials, one of the parameters, is the amount of dark matter in the early universe. And without the right amount of dark matter, this does not match at all. I can prove it. So you can actually go, this is a nice little demo that someone has made where you can simulate your own universe. Where what you've got here, here's my cursor, you can play with the amount of regular matter and the amount of dark matter and the amount of dark energy in your universe. So let's say that we want a completely classical universe, right? So we want a universe that's full of normal matter and no dark matter, because that's too weird, and definitely no dark energy, because like who knows what's going on with that. We'll get rid of all the stuff, we'll have a completely sensible universe. The CMB looks nothing like the CMB that we actually see. A completely classical universe full of normal matter and none of this strange stuff that we don't understand looks completely different to what we actually observe on the sky. The only way to match what we actually see, I'm going to see if I can remember these numbers off the top of my head, is 5% normal matter, 27.5% dark matter, and 67.5% dark energy. And then you get this perfect match. And it would be an extraordinary coincidence. That ratio between the amount of dark matter and the amount of normal matter is exactly what we see in gravitational lensing. It's exactly what explains the clusters of galaxies and the spinning galaxies. So it's time and time again, right? If this was a court case, it'd be a slam dunk. We're just seeing this evidence over and over and over again. So it is sort of overwhelming consensus at this point that the universe is full of some strange, heavy stuff that we don't understand. Okay, so what is it? This is the question. This part of the talk will be shorter. So for the longest time, at least in the past, astronomers had hopes that dark matter would turn out to be something fairly conventional. One of the early ideas was that it was just faint stars, right? We know that there is a distribution in the sizes of stars where there are very, very few enormous stars, and then there are more medium-sized stars, and there are vast numbers of small stars. Astronomers wonder, well, maybe there's just loads of those, right? If we just go to tiny stars that are so faint we can't see them in our telescopes, maybe they just outnumber the normal stars sort of millions to one, and the weight of all those invisible stars that are too tiny to see explains dark matter. This is a very nice idea. There's an astronomer called Catherine Fries who led on this idea. Unfortunately, the Hubble Space Telescope came along and showed us these stars don't exist. So yeah, that doesn't work. The next idea was, well, maybe if they're not stars themselves, maybe they're like failed stars or things that can't quite ignite. Something like Jupiter, for example. Jupiter is a ball of hydrogen. It's made of the same substance as the stars. Because it's too small to burn, it doesn't glow. It doesn't show up in our telescopes. So maybe dark matter just could be countless trillions of Jupiter-type things, these blobs of hydrogen that don't burn, and so we can't see them. But if there's enough of them, the weight of them could be dark matter. But that doesn't work either, unfortunately. The way they were able to test that was by looking at some very, very distant stars in the Magellanic Clouds, one of the dwarf galaxies orbiting the Milky Way, and waiting for these sort of mysterious Jupiter-y sized things to drift between you and a background star in a way that you could detect. And there would have to be so many of them that these like occultations of distant stars would be really common, and they just weren't. So that doesn't work either. So yeah, it can't be stars. It can't be like failed stars, like Jupiter things. We know that from those sort of star blanking out experiments, that whatever one bit of dark matter weighs, it has to be less than the moon. And I know less than the moon is a lot of wiggle room, right? But it means it can't be anything made of hydrogen, like a star or a gas planet. It can't really be asteroids or dust, mainly because asteroids and dust are made of heavy elements like carbon and silicon, and those heavy elements are generated inside stars, and you can't have like the waste generated by stars outweighing the stars 10 times over, right? So that doesn't work. So can't be stars, can't be failed stars, can't be dust, can't be asteroids, can't be planets. Basically, the only way is down at this point. So yeah, our best idea is that for some substance which interacts through gravity, which it has to, remember, that's how we know it's there, but it ignores the electromagnetic force, is some kind of particle. And so this is our great hope, that there is some particle out there that we've not yet discovered that fills the universe and interacts with gravity but ignores the electromagnetic force. Because we know there are loads of particles out there, right? Anyone that studied physics in school will remember all the particles hanging on the wall. There's the familiar things that make up our bodies, like protons and neutrons and electrons, and there's sort of funky things that they make inside particle colliders, like muons and tauons and neutrinos and all these sorts of things. There's a vast zoo of particles that we know about. So what we hope, is that there is one more particle that we haven't discovered yet that sort of speaks to gravity, that has some weight, but ignores the electromagnetic force. And for the longest time, our best guess, best hope has been something called a WIMP. So this is the leftover half of a joke that doesn't work anymore. So back in the 90s, the two best models we had for dark matter were a particle, which we called a WIMP, and then one of these like failed star type things in the outskirts of galaxies, and they were called massively compact halo objects, or MACHOs. And so, yeah, astronomers had great fun with this showdown between WIMPs and machos, right? But machos aren't real, and we're just left with WIMPs, unfortunately. So a WIMP is our sort of, for the longest time, has been our favored guess for what dark matter actually is, one of these particles that fills the universe. The problem is they are very difficult to detect, because by definition, right, WIMPs or whatever dark matter is, does not absorb or emit light. We've never seen a peep of it in any telescope. It has to completely ignore the electromagnetic force. But the problem is any particle that completely ignores the electromagnetic force will travel straight through ordinary matter, which makes it very hard to find. The reason for this, you might have heard the facts that matter is mostly empty space. I remember hearing that when I was a kid. That I think the classic thing is if an atom is St. Paul's Cathedral, the nucleus is a bit of a grain of sand in the center or something. Atoms are like 99.999% empty space. I remember hearing this when I was little and thinking, well, why am I solid then? Why is anything solid? If I'm empty space and this table's empty space, why doesn't my hand just go straight through it? And the answer is that the solid nature of matter is an electromagnetic effect. When I'm knocking on this table, what's actually happening is that the electrons in my hand are repelling the electrons in the table. This is an electromagnetic interaction. If I could switch off the electromagnetic force in my hand, it would just whiz straight through the table, right? I might be a bit distracted by my body dissolving into mist, right? But you get the idea. If without the electromagnetic force, matter is not solid. And so any particle that ignores the electromagnetic force can just go straight through solid matter. And that's very difficult if you're trying to detect it, right? Because you can spend £100 million on a very fancy dark matter detecting machine, and then your dark matter particle is just going to whiz straight through and out the other side. It's like trying to catch a fish with, we're using a net with 100-meter wide holes or something. It just doesn't work. There is hope, or we hope there is hope. So if I go back to the WIMP, so WIMP stands for weakly interacting massive particles. So the particle bit is hopefully obvious. Massive, we sort of have reasons to believe that the dark matter particle is very, very heavy, hundreds of times bigger than a proton. The weakly interacting bit has been the great hope of astronomers for the longest time. So there are four fundamental forces in the universe, right? There's gravity that we've been talking about this whole time, and there's the electromagnetic force. And there's also the strong and the weak forces that we don't notice in our day-to-day lives because they just hang out in the center of atomic nuclei and stick them together. So there are reasons to believe that a particle that interacts only with gravity and the weak force sort of nicely explains dark matter. And this gives a hope because matter is mostly empty space, of course, and so 99.99999 whatever of dark matter particles are going to whiz through atoms and out the other side. But that incredibly rare 1 in 100 trillion or whatever that gets a direct hit on the nucleus is going to come into contact with the weak nuclear force and maybe cause an interaction. And so this has been the hope for the longest time, to wait for these incredibly rare interactions between a dark matter particle and the nucleus of an atom. So the way that you build a dark matter detection telescope is you go deep underground, first of all, because you want to filter out all the noise and the junk from the surface, because dark matter particles can go straight through solid matter, right? So going 10 miles underground is no problem for dark matter. So you go deep underground. You want to build a big dark matter trap. And so what often gets used is like cleaning fluids. They're often sort of heavy chemicals that have nice big nuclei that make nice big targets for your dark matter particle, and they're fairly cheap to obtain. So you go deep underground, you buy an old gold mine or an old abandoned subway station or something, you get 10,000 liters of cleaning fluid, and then you just watch it for a really long time. And that's what we've been doing for decades at this point, to try and find dark matter. This is one of them. This is called Xenon. This is in an old subway station underneath the Alps in Italy. They look very science fiction-y. And so far, they've found nothing. So, yeah, it's getting to the point. WIMPs are slightly going out of fashion for a couple of reasons. WIMPs looked like an absolutely brilliant solution to the dark matter problem when they were first hypothesized. But we've effectively searched for the kind of WIMP that will beautifully explain the dark matter problem, and it seems like they don't exist. Our sort of great hope has turned out to be not very much hope at all. The problem with WIMP experiments these days is that they're getting to the point where even if there is a WIMP dark matter particle out there, we might not be able to find it. So this is what a dark matter detection experiment sort of does. So you have this sort of this parameter space, this plane, where you can sort of graph the mass of the dark matter particle, how heavy it is, versus sort of the size of it, how big it is. And any given dark matter detection experiment will sort of take a bite out of this and say, it's not above here. We've ruled out this part of the space. And then over the years, the dark matter detection experiments have just come in all different shapes and sizes and different configurations and have taken different bites out of this parameter space. And we can sort of say, wherever dark matter is hiding, it's not above any of these lines. The problem is that at the bottom of this graph is lurking something that astronomers call the neutrino fog. So neutrinos are these very, very light neutral particles that stream out of the sun. Every single solar fusion reaction that creates the heat and light that we need to survive also creates neutrinos. The sun is this vast source of neutrinos. And neutrinos are sort of, in some ways, are similar to a dark matter kind of thing, right? They're these particles that stream through empty space and can travel straight through matter. And once you get a sufficiently sensitive dark matter experiment, neutrinos start getting in the way. And we're kind of at the point now where even if the WIMP particle was down here, the neutrinos from the sun would just deafen us. It'd be a bit like trying to listen to a whisper from across the stadium during like a rock concert or something. There'd just be absolutely no hope at all. The reason this is like my cartoon graph, by the way. The reason I showed you this rather than the real one is that I didn't want you to run. I didn't want to just put this up and have you just run for the doors. But now you can read this, right? So now these are all the different dark matter detection experiments, and the neutrino fog is sort of getting to the point where it's going to be interfering with experiments. Luckily, like scientists are not out of ideas. There are lots of different alternative dark matter candidates that people are getting very excited about. The one that a lot of my colleagues are working on at the moment are called axions. So axions are very exciting. They were originally invented by the particle physicists. We don't know if they exist or not. They were invented back in the 70s as a solution to particle physics, this particular symmetry breaking problem in particle physics. They're called axions. It's a brand of washing powder. They were supposed to wash away the problems, right? That was the idea. But it turns out you get a 2-for-1 with axions. They nicely solve this particle physics problem, and they could potentially be a dark matter candidate as well. So searches for axions in the last few years have been picking up. We're involved in some in Cambridge. My colleague Hiranya Peris, I think, was here last year talking about her search for axions. The nice thing about doing axion searches is that it's much cheaper. You don't have to buy an old gold mine and just stare at 10,000 liters of cleaning fluid. Axions are very, very small and light. They're so small and light that their quantum mechanical wavelength is actually quite big. And so you can sort of hunt for axions on the tabletop, basically. You can build a resonance chamber and just try and capture axions in the act on your desktop. So much cheaper, millions rather than hundreds of millions, which is very, very appealing. So yeah, axion searches are just getting going. There's all kinds of alternative explanations for dark matter, things like primordial black holes and all kinds of exotic things. We don't know, what the best one is going to be. So this is the point of the talk where I admit that I don't have an ending to this, right? I wish I had an ending to this talk, genuinely. I cannot wait until I can give a talk about dark matter and I get to lay out all the evidence and take you along the journey. Then I get to sort of unveil the answer and say, and this is what the solution was all along. A lot of the time when you sort of read about stories of science, this is the way they're told, right? They're told in retrospect. You have the problem, then you have all the attempts at the solution, and then you get the solution. You get this great resolution. You get to find out what the answer is. But we're not quite there with dark matter. And so this is sort of how it feels to do science from the inside, right? You have the problems, and you have the attempted solutions, and you don't know what the answer is going to be. I think out of all the problems I genuinely hope are solved within my scientific career, dark matter, I think, is probably number one. I can't wait to find out what it is. I'm very jealous of the particle physicists. If you remember, when the LHC came online, it had two main headline goals, right? It was supposed to find the Higgs boson, which was the holy grail of particle physics, and it was supposed to find the WIMP, the dark matter particle, the holy grail for cosmology. And the particle physicists got their holy grail, right? They found the Higgs boson, and it was great. And yeah, and we're still hunting for dark matter. Hopefully every day it gets closer, right? And I genuinely can't wait to hear what the answer is. And I'm going to finish there. Thank you.